Hello students, welcome to Inside Physics. I am Srinivas. Today we are going to discuss magnetism and matter. In this we are going to discuss about the bar magnet. So magnetism and matter. So they are both linked to each other. So matter, that means liquids, solids and gases. So in this matter and these kind of substances who generate or who exhibit magnetism are generally called magnetic materials. So in matter, in the universe we have so many magnetic materials who exhibit magnetism. Now today we will discuss some properties of bar magnets and its characteristics regarding field lines and its resemblance with the solenoid, how it resembles, and the analogy with the solenoid. Okay, so what is a bar magnet? And we are not going into any history of the magnetism. Just we will focus on bar magnet. Previously, in ancient days, Einstein was given a bar magnet by one of his relatives. So he played with it endlessly and he found out some interesting things when he was playing with a bar magnet, and it was created so much fascination in Einstein. So that's the beginning of the journey of magnetism. Okay, now in our present context, how to characterize a bar magnet? So simply we can draw a bar like structure which is having a south pole and north pole. So this is called south pole, this is north pole. And to characterize the south pole and north pole and the bar magnet, if you pour some iron filings on a bar magnet, and the iron filings, why iron filings means the iron filings will be attracted because of the magnetism with this bar magnet, and they will arrange themselves in such an order like this around these poles. So this order is like the magnetic field lines, and they will arrange themselves in this order, and with this arrangement we can say the iron filings are arranged in this way, and there are two poles with the magnet, one is named as south and one is named as north. Okay, so in this way what we can consider is a bar magnet is having a two poles and with an property of magnetism. See, magnetism is a property with which a material can attract some materials and some elements. So without touching the element, and there is no physical contact between the magnets and the elements with they are getting attracted. Okay. So now we discuss about the bar magnet and its field lines. So what is a field line? So we'll discuss about the field lines here, and we will draw to draw the field lines around a bar magnet so that we can identify some characteristics of field lines. So magnetic field lines. Unlike the electrostatic lines of force, these are not called magnetic lines of force. These are called magnetic field lines. Why? Because in electrostatic field lines, we know around a charge there will be field lines generated in every direction from a point source charge. Okay. But here The in electrostatic, the field line is a path followed by a unit test positive charge. That's why it is called the electric line of force. The force experienced by a unit test positive charge along the path of a electric field line. Okay, so this will be ending up at a negative charge. So this is the source charge, this is the sink charge. So here, in this way, we demonstrated the electric lines of force, but now we are going to see what are the characteristics of magnetic field lines. So, the magnetic field lines will form closed loop starting from the north pole outside the magnet and end at south pole outside the magnet, and inside the magnet they will be directed from south to north, and outside the magnet they are directed from north to south. So in this way, the magnetic field lines will be generated from the north pole, and they will be forming closed loops, continuous closed loops, so that this loop is a continuous loop, there is no cut in between. So all the field lines emanating from the north pole will obviously form closed loops only. Okay, so this is the main characteristics of a magnetic field line. Okay, if you observe these field lines, so what is the direction of the field at any particular point on this field line? If you want to know the direction of magnetic field at a particular point, suppose P, so you can draw a tangent at this point. So this direction of the tangent gives the direction of the magnetic field B bar generated by this bar magnet. So this is the second characteristics, the direction of magnetic field given by a tangent drawn to the magnetic field line at any particular point. Here, if you want to know the direction, you can draw another tangent here, and this gives the direction of magnetic field at this point. And here, if you draw another tangent, this will be the direction. Here, the tangent direction will be towards the south pole. Here, the tangent direction will be this side. In this way, the field direction is from north pole to south pole outside the magnet, and south pole to north pole inside the magnet. So if you observe these field lines, they do not intersect at any point of time or at any point. Okay, why they do not intersect means, if they do intersect at any point in their path, that means you can draw a tangent to find the direction of the magnetic field. At that point, you will find two directions for the magnetic field. So suppose if any field line is crossing another magnetic field line, so at the point of intersection, you may find two directions for the field, which is not possible and which is an absurd. So we say that magnetic field lines do not cross each other. Okay, they will never intersect each other. Okay, so these are the some of the characteristics of magnetic field lines, and you can draw these magnetic field lines by placing a compass needle nearby the bar magnet. So the compass needle will be deflected at different points in a different orientations. So by analyzing the magnetic needle, suppose if you put a magnetic needle here, a magnetic compass needle, it will show some orientation because of the magnetic field generated by this bar magnet. So every point you place this magnetic compass needle successive points, you analyze the orientation of the north pole and south pole. Generally, the north pole of a compass needle will be directed towards the geographic north of the earth, but near the bar magnet, the compass needle, the north pole of the compass needle will be directed towards the south pole of the bar magnet. But when you consider the earth geographic south and north, the south pole of the magnetic compass needle will be directed towards the south of the geographic south of the earth. Okay, the north pole of magnetic needle will be directed towards the geographic north of the earth. So here the magnetic compass needle is nearby a bar magnet, so that it will be deflected because of the magnetism of the bar magnet. So the because of the orientations, if you analyze the orientations north and south in this way, what are the orientation of, suppose, so if you analyze these all the points and draw a magnetic field line, it will be look like this, what we have drawn. So the lines will be making a path like this. So this is the way of marking the magnetic field lines around a bar magnet. So this is also applicable to a solenoid, which is almost analogous to a bar magnet. So if you place a magnetic compass needle nearby a solenoid also, you will get the same field lines as generated by the bar magnet. Okay, and if you observe the bar magnet and the field lines emanating from north pole are quite dense. If you take an area here, they are quite dense here, and if you take an area, suppose at this point, the magnetic field lines, the number of magnetic field lines are less in this area, and this is area 2, this is area 1. Just we suppose for our assumption, in the area 2 the field lines are more, in this area 1 the field lines are less. So if the number of field lines passing through an area of cross section is more, we can say the field intensity is more in this area, and the field intensity is less in the area where the number of lines are less. Okay, so in this way we can analyze the magnetic field lines. Now we will see how a bar magnet is analogous to a solenoid. Okay, what is the analogy between the bar magnet and a solenoid? We already seen that a solenoid can generate a magnetic field lines like a bar magnet, and here I have drawn a diagram for a solenoid which is having n number of turns. And here, now what is the analogy we are going to discuss means, we will calculate the magnetic field of this solenoid on the axial line of this solenoid, and at far distances, suppose we take a distance large compared to a radius of the solenoid, and the length of the solenoid, we take the distance r, we take a point p on the axial line from the center of the solenoid. So at far distances, the analogy is the magnetic field generated by a solenoid resembles a bar magnet at greater distances. That's what we want to prove here. And before that, there are one or two analogies between the bar magnet and solenoid. if you cut a bar magnet, suppose if you take a bar magnet like this, north pole and south pole, if you cut the bar magnet into two pieces, it will again form two similar bar magnets with this kind of arrangement of north south and north south poles. So an ideal single north pole or south pole cannot be found, and there will be two poles arranged in a similar order, and this broken two pieces will act as two separate magnets with lesser magnetic properties. Even though they form two magnetic pieces, the magnetic properties such like magnetic intensity and the number of field lines per unit area may decrease because of the arrangement that we have broken this bar magnet. In a similar way, if you cut this solenoid into two pieces, it will also be behave like a two solenoid system, and each solenoid will behave like an individual solenoid, and the magnetic field lines as per the large solenoid, it will enter in from one face and leave from the other face, and from the second part also it will leave from the one surface and enter from the other surface. So this is the one analogy between solenoid and the bar magnet. So now we prove the magnetic field on the axial line of a solenoid at far distances is equivalent to a bar magnet. Okay, now we know the magnetism by Ampere's theory, all the magnetic properties can be explained by current carrying loops, circulating current. So in this way, a loop can be considered as a continuous solenoid with n number of turns. A single loop is having one turn, and the continuous loops having n number of loops can be considered as a solenoid. We know that magnetic dipole moment of a current carrying loop we have discussed in the previous sections. That means this is NIA, the magnetic dipole moment of a current carrying loop. This is N is number of turns in the loop, current passing through the loop, and this is the area of cross section of the current carrying loop. So magnetic dipole moment. So here next one, in the previous section we have seen that the magnetic field generated by a current carrying loop on the axial line is nothing but dB is equal to mu naught n I dx a square by 2 into r minus x whole square plus a square 3 by 2. So here with this relation I will explain some of the terms attached to this diagram. Here A is the radius of the turns in the solenoid, and R is the distance of the point we have taken on the axial line from center of the solenoid. If you consider the length of the solenoid as 2L, so this is half, this is second half, and the half of the length is considered as L. So for calculating the magnetic field due to this entire solenoid at this point P, first we considered that this is a small area of the loop which is having a length dx. Okay, and this loop is nearer to the center with the distance x. Okay, if you observe this, Why we have taken this loop? Because we will consider the loop as a current carrying circular loop, single loop, and we will calculate the magnetic field because of this on the axial line at a point P. And when we integrate the relation between the limits minus L to plus L, then we can get the magnetic field due to entire solenoid at the point P. This is the method we actually followed when we have derived the magnetic field due to a current carrying loop. Okay. Here, see dB, small electric field generated due to the current element we have taken, a single loop, small length loop we have taken, and here the A is the radius of solenoid, r is the distance from the center to the point P. See, x is the distance between the current element and the center. So here, if you observe, we can write this relation as mu naught ni a square. So this is the magnetic field due to a single loop with length, small length dx. Now we need to find the magnetic field due to entire solenoid. For that, we will integrate the terms here between the limits minus L2 plus L, which is the term that needs to be integrated. Here this is dx. Dx is the length of the loop, and we want to extend this length to the entire solenoid, which is having a limits from minus L to plus L. If you consider this as an origin, this length is L, this is minus L. So the total length is 2L. So between minus L to plus L, we can consider integrate the length dx. So rest of the terms will be same, and we can write here okay. So we have already told you we have taken a point very far away at larger distance, so that the distance r is far greater than a, and this distance r is far greater than x. Okay. So with this relation, we can ignore the elements, the distances x and a. So when r is very greater than a and r is far greater than x, we can ignore the terms x and a, and we can write the rest of the relation in a manner so that x is and a are ignored. So this x we can put it as 0, and a we can take it as 0. So what happens to this relation? Ni a square by 2 into this will become r square. Okay. So r square whole to the power of 3 by 2. X and a will become 0. So this is minus L2 plus L dx. Okay. So this is dB. Now, so now we are going to get the entire magnetic field due to the solenoid. Now the terms will become mu naught Ni a square by 2 into this r square whole power 3 by 2 will become r cube. Okay. And now this integration if you perform the integration, this will become x between minus L and plus L. Okay. So this term will become mu naught n I a square into this will become 2L by 2R cube. Okay. Now we will multiply the numerator and denominator with 4 pi. Okay. We will multiply the numerator and denominator with 4 pi. Then here we can write mu naught by 4 pi into, see, this n into L. Okay. And I, this we can write as pi a square by R cube. Okay. And here there will be, if you write 4 pi by 4 pi and 2 gets cancelled, there will be one more 2 here. Okay. So if you observe this one, why I have written 1 mu naught by 4 pi, how means I have multiplied the numerator and denominator with 4 pi. Okay. Then from this I have written mu naught by 4 pi, which is a proportionality constant when we are calculating the magnetic fields. So NL I into pi a square. This again can write it as mu naught by 4 pi. NL is nothing but N is number of turns per unit length into length 2L. This 2 into NL, this becomes 2L. That means total length of the solenoid. This is, we can write as total number of turns and I into A. Okay. So this pi a 2L 2 gets cancelled and there will be, here we can write it as 2 into, this will become another 2 in okay. So NIA 2 NIA by R cube. Okay. Now here if you observe this relation, it will become mu naught by 4 pi 2m. I will write m. What is m? Magnetic dipole moment, which we have already discussed. Magnetic dipole moment of a current carrying loop is NIA. So magnetic dipole moment by R cube, mu naught by 4 pi into 2m by R cube. This is the total magnetic field generated by a solenoid having n number of turns on the axial line at a point P taken at a greater distance from the center of the solenoid. So this magnetic field exactly resembles the magnetic field generated by a bar magnet. So we have an analogy with solenoid. Why? Because the bar magnet can be taken as an equivalent to a solenoid when we consider the field at some greater distance on the axial line at a point. Okay. So this is how we will analyze a bar magnet and its characteristics, the field lines, how to draw the field lines, its analogy with the solenoid. Okay. So the unit for the magnetic field here is Tesla. unit for the magnetic field is Tesla. So in the next sessions, we are going to discuss about the characteristics of some more magnetic materials. Okay, thank you.